Good morning, everyone. Thank you for being here. Welcome to our final webinar of the project. This is our last one. It's called From Biowaste to Green Steel, Catalytic Pyrolysis and Industrial Decarbonization. And we have a very esteemed and respected panel today, a lot of collaborators from the project. So the first one who's going to be framing the project, so you know a little bit more about it, is David Chiaramonti. Uh, Please, David, the floor is yours.
Thank you, Fernando. Thank you, Contactica, for organizing this, and thanks to the partners for this long journey along this project, which is extremely challenging. Yeah, as Fernando said, just let me frame the reason why the Commission is putting so much attention to defossilizing the industry and producing green hydrogen at competitive cost. The issue is almost daily present on media and newspaper because as we approach targets, as the volume increase, the cost for the industry and therefore for the customers and the downstream processing industry in Europe are becoming higher and higher. And in parallel to renewable hydrogen from solar and wind, in the effort of reducing cost, as well as in the effort of replacing fossil coal, there are other routes that can be explored, and that looks very promising. That's the example of biocoal from waste materials and the use of this product, this bio-based product and waste-based product, as a catalyst for hydrogen generation from biomethane. No matter, I mean, it's important to remind that biomethane, according to the latest studies in Brussels, has the largest potential so far, which is 15 and 45 million tonal equivalent, respectively, from 2030 ahead. We're dealing with the largest probably potential that exists so far for internal European production and not import of these energy vectors. The project, as the speakers will present today, is targeting at least two main goals. One is to elaborate the waste material like wastewater sludge or bio residues, bioproducts, into a carbonaceous material suitable for the use in industry, but also suitable for its use as a catalyst. And that's the second goal in the methane pyrolysis, biomethane pyrolysis actually, to generate solid carbon and hydrogen. The carbon goes to the, well, let's say both products goes to the end use industry, even if certainly carbon hydrogen could also have in the future other destination. To conclude this introductory framing speech, the goal is to reduce the cost of hydrogen also here. And this seems to be possible thanks to the fact that we actually have two products coming from our process. One is the carbon, the other is the hydrogen. While if you compare with the let's say, more conventional routes based on electrolysis to hydrogen, there's one main product, which is hydrogen itself. So thanks to the fact that we have more than one product, and then we need also to add the carbon credits, which are associated in the carbon value chain, we can target production prices for hydrogen that are approaching the cost of hydrogen from the conventional natural gas reforming. In a nutshell, this is the reason why this route was selected, and now we can definitely go through the work that has been done on all the different technical aspects, the pilot unit, proof of concept that has been built, and and some high-level results. So, Fernando, I'll give you the floor back to you.
Thank you very much, David. So yes, that was a great introduction of the project. And now we're gonna go with our first speaker of the day, which is Andrea Salimbeni. He's gonna be speaking about decarbonization of steel manufacturing sector. So Andrea, please, the floor is yours now, and go ahead whenever you want.
Thanks, Fernando. I'm sharing my presentation. Let me know if you see the first slide in presentation mode.
We can see it, but it's not in presentation mode.
Okay. No? Can you see it moving, but not in presentation mode? Just
Exactly, yeah.
Just a second. Now?
Yeah, still the same. Okay, now. Yes,
Okay,
perfect.
great. So, yeah, this is an introduction to the objective of H2STEEL project, which is decarbonizing the steel sector. But it want to be a very general lecture about the steel sector and how to decarbonize it, what are the main barriers. The intensive emission of CO2 derived from the steel making is mainly related to the traditional steel making process, so the one using blast furnaces and lots of coke and fossil coal to be used as reducing agent for transforming iron or in iron metal. So the average CO2 emission per ton of steel, which is in the range of 2.3 tons of CO2 per ton of steel, is mainly related to the traditional iron making and steel making process. So the process where iron ore is injected together with coke in the tall blast furnaces to produce pig iron. Then we will see that there are already solutions and processes with lower footprint, carbon footprint, but they are still emerging and they not fully avoid CO2 emission. So the primary source of CO2 in the steel making process is due to the use and consumption of fossil coal. Fossil coal is can be of different quality, and the Van Crevelen diagram is the best way to summarize different characteristics and quality of fossil coals. We go from the anthracite, so the highest rank coal, low volatile, high carbon, to the bituminous coal, so the this area, which is including coals of even higher volatility, up to the lignin class. Lignin and peat represent fossil carbon sources which have not finalized the carbonification process, and that is why they are still volatile and not that considered anymore as coal. So all these coals are used in the steel making process, but these, the coal and the anthracite, are those really used. Anthracite is used mainly in the sintering process and as a PCI. The coal is used both as a fuel and as a source of coke. Coke is the process where coal is pyrolyzed at 900 degrees to produce a particular high strength, low volatile coal material to be used in blast furnaces. So these are the coal that we need to replace if we want to decarbonize the steel sector. Just to give some idea, we did some studies based on literature and on Eurocoal statistics. The crude steel produced is in the range of 136 million tons per year in Europe. The total coal consumption is in the range of 56-60 million tons per year. As you can see, this column describes the traditional process and the new electric arc furnace based process. The traditional process is, said, iron and steel making route, where the iron ore, so the mineral is processed in blast furnaces with the consumption of coke and coal as a fuel to produce pig iron. And this is consuming most of the coal of the steel sector. The electric arc furnaces are used mainly to recycle steel scrap, so the consumption of coal is much less. But anyhow, we have as a target likely 50 million tons per year of coal to replace. Why we need to replace that? Professor Chiramonti already mentioned that, so I will go quite quickly. We have about 3 million tons of CO2, 3 billion tons of CO2 emitted in Europe, and the steel sector and the industry sector is responsible for quite a lot of this share. Fortunately, we have a system which is named ETS, which is putting a price on CO2 in the form of credits to buy. So companies like steel companies have to buy CO2 certificates emitted by the ETS program every year, and they have to buy 1 certificate per ton of CO2 they emit. And nowadays, the price, this was last 2025, was in the range of 71 euro per ton. On average, we can say now it's in the range of 80, and we are going towards 100 in the next years. Just to give an idea, the ETS generated about 43 billion euro revenues only in 2023, and we expect to generate even more in the next years when it will be extended to more sectors. Of course, these price on CO2 produce represent an issue for steel sectors, companies, as they have to pay likely a tax, additional tax to their production process. And that is why the biocoal compared to the fossil coal can be a solution. Because if we replace fossil coal with a biocoal, probably we can reduce the CO2 emission, and for companies, we can reduce the amount of certificates to buy. So the ETS is the way we have to make biocoal competitive with fossil coal. And it is basically the target of this project is to produce bio-based reducing agents for the steel sector to improve the economics and the sustainability. So, as I was saying before, we have a traditional steelmaking and a more modern steelmaking process. Traditional steelmaking means we consume coal for everything. We have the blast furnace, which is our pig iron production unit. How the blast furnace work, I will explain later, but just to give you an idea, the consumption of coal is in the range of 700 kilo per ton of steel or hot metal produced, distributed as follows: the coke oven to produce coke, the pulverized coal to be injected, and the sintering process which is needed to transform the mineral, the iron ore, into a feedstock suitable for the blast furnace. So in a blast furnace, the consumption of coke is in the range of 300, 350 kilo per ton of hot metal, while the coal injected as pulverized coal is in the range of 120 kilo per ton of hot metal, which is quite a lot. The pulverized coal injected has the role of producing CO, so that we enable the reduction of iron ore, iron oxide into iron metal and CO2. The coke has a double role of producing CO while gasifying, but also to maintain a porous layer between the iron ore which is injected in the furnace, so that the gas can pass through and the production of gas can enable the reduction of iron ore into iron. To do that, the coal used, it is considered high quality coal, where the volatiles are quite low, between 10 and 20%, and the carbon content of the coal should be high. Between 65 and 80% is something that is acceptable. These are example of coals commonly used in blast furnaces. These are the coal that we have to replace. The coke oven is, I will be quick here, it's a pyrolyzer of coal. In these reactors, the fossil coal, in particular vitrinite, is processed at 900 degrees for likely 19 or 24 hours in almost absence of oxygen. These are the chamber where the coal is charged, and these are the chambers where heat is produced by burning the gas. In this case, at these conditions, the specific coking coal like vitrinite and liptinite becomes fluid and degrades, producing a highly porous, really strong carbon-rich material, which is named coke, which present much more structural properties and compression strength and resistance than fossil coal. So in this case, these are the composition of the coal used in a mixture to produce coke. As you can see, volatiles are higher compared to those of the coal used for injection. So we discussed about coal, but coal is not the only reducing agent. Hydrogen is becoming really interesting because it's a reducing agent that is producing water vapor and not CO2 when it reacts. And that is why the direct reduction of iron is taking attention, and it is part of this project. What is direct reduction of iron? Direct reduction of iron means that we decouple the production of iron metal to the melting of the iron metal. In a blast furnace, the iron ore is simultaneously, we can say, reduced and melted, producing hot metal with carbon inside. In the direct reduction or pre-reduction of iron, we have iron ore which is injected in a reactor staying at likely 900 degrees, so much lower than the iron melting point. At this temperature and with the injection of a reducing agent like hydrogen, but it could be also methane or CO, the iron is reduced to iron metal, producing, in this case with hydrogen, only water vapor as a byproduct, as a gas. In this specific condition, the iron is reduced but not melted. And that is why after being reduced as a metal, it can go to the melting furnace, which is an electric arc or a submerged arc furnace, where the carbon is also added to produce the steel. That is the difference. So direct reduction of iron means decoupling the iron reduction from the iron melting, and it enables to reduce the emissions, in particular when hydrogen is used. This is one of the last points. Electric arc furnaces are used when the iron is already as a metal. So they can be used with iron metal, so a direct reduction, or to remelt the steel scrap. So it's the process is simple. Electric arc is used to give the energy to melt the material, the scrap or the reduced iron is melted and the carbon, the coal is added to adjust the carbon content in the hot metal, because it's always important to remember steel is an alloy of carbon and iron. And that is an example of the quality of the coal used in electric arc furnaces. Can be more or less volatile based on the specific target and the specific quality of the steel that we want to produce. So, what is the target? We need to produce a coal with reliable quality to replace fossil one. So we have to produce something of low volatile content, high carbon content, and in particular, we need to avoid to have contaminants that are critical for the steel quality, like phosphorus, potassium, sodium, and sulfur. That is our target. Do we want to decarbonize the steel sector? If we want to do that, we need to introduce new reducing agents like hydrogen and bio-based coal. And that is what H2STEEL is doing. Regarding the electric arc furnaces, the limits are the same. If we want high quality steel, we need to produce a coal alternative with low volatile, high carbon, and low contaminants, low sulfur, low phosphorus, low zinc, low lead. So both in traditional steelmaking and in electric arc furnaces, carbon must be injected in different quantities, but it is needed to be used as a carbon source in the alloy, in the steel. In traditional steelmaking, the blast furnace is an equipment that cannot avoid too much the emission of CO2 because it cannot be integrated directly with a hydrogen as reducing agent, or if not partially. So biocoal can replace fossil coal in the coking process at a maximum of 15%, as a pulverized coal at 100%, and in sintering process the same. In electric arc furnaces, biocoal as well as the fossil coal can be used as 100% alternative as carburizer, as reducing agents, and as foaming agents. So that is the conclusion of this presentation is we can replace fossil coal with biocoal. We can produce green hydrogen to be used in the in DRI, and that is what H2STEEL is trying to do. Combine the production of green hydrogen and biocoal for the steel sector. Thanks so much.
Okay, thank you very much, Andrea. I don't see any questions here, but as I was saying in the chat, if you have any questions and you want to ask them, please write them down and we'll have them answered at the end of the presentations, okay? So our next speaker is Alessio Riorda. He's going to be speaking about methane catalytic pyrolysis for hydrogen and carbon recovery. So Alessio, please, the floor is yours. We can see your screen, but yeah, now perfect.
Now is the presentation mode? Oh, great. So now I will really briefly introduce one of the technology of the H2STEEL project, that is the methane catalytic pyrolysis or cracking or decomposition, different name for at the end the same reaction, with the goal of producing hydrogen and solid carbon. But before to enter, now it's changing also slides. Okay, before to enter into the H2STEEL topics, let's do a brief theoretical lesson about the thermodynamics of the process and also the different kind of technologies. So first of all, the thermodynamics behind the methane cracking. As you can see here, the methane cracking reaction is a reaction where the methane is just divided, decomposed into hydrogen, gaseous hydrogen, and solid carbon. And this is an endothermic reaction. It means, of course, that you need to give energy to the methane to then crack into hydrogen. And as you can see in the first plot in the left, is an endothermic reaction. It means that you need to have higher temperature to have a good conversion of the methane. So if you increase the temperature, you're increasing the conversion of the methane. And the second point is that during the reaction, we have also an increase of the moles of the molecules, because you are going from 1 mole of methane up to 2 mole of hydrogen, so you are increasing the volume. It means that, of course, the pressure is avoiding the expansion of the gases. So if you have a higher pressure, your conversion will be lower. And this clearly represented in the second plot of the slide, where with the higher pressure, you have a lower conversion. So let's say that, summarizing, we need to have higher temperature and lower pressure to then have a methane cracking reaction, a good methane cracking reaction. So which are instead the technology that we can use to do that? First of all, we can divide the technologies into non-catalytic and catalytic cracking. With non-catalytic, of course, we have, as I said, give to the methane the energy to crack into hydrogen and solid carbon. And to do that, you can do it in thermal way, just burning something or electrical heating to heat up the methane and then crack the molecule. Or you can do that with other technologies like microwave or plasma. But these are just based on the thermal action, so the heat that you're giving to the material. Instead, if you want to use a catalytic process, you can use a catalyst to reduce the temperature needed for the cracking. In that case, you can use different kind of catalysts, like metal catalyst, nickel, cobalt, iron, or a carbon-based catalyst, but we will see that later. Then there are also hybrid processes like molten metals or salts that have both the actions, but these are not part of the presentation. Focusing on the catalytic cracking, as you can see here, you can have different metals between them. The most used in literature are iron, cobalt, and nickel. And you have also here an overview of the prices of the material. But the most important part is the first plot you can see, where is represented the temperature range in which any of this kind of catalyst or processes can work. For example, the non-catalytic reaction, as I said, you need higher temperature that are going from 1,000 over 1,600. Instead, if you're using a catalyst like carbon, iron, cobalt, you can decrease the temperature and obtain the same results at the same time. For example, the carbon one can work between 800 and 1,000, or the nickel is the one with the lower temperature because it's more efficient in the conversion, but at the same time can have problem with temperature like sintering or something like that. In the other two graphs that you can see here, that represented the conversion dependent to the temperature and also the stability of the catalyst. This is another good point that we will discuss in the next slide. Why? Because, as I said, the reaction is breaking the methane into gaseous hydrogen and solid carbon. And the solid carbon have to go somewhere. In this case, if you are doing a catalytic reaction, the solid carbon is depositing on the catalyst. And this is the process that leads to the deactivation of the catalyst. Because when it's covered of solid carbon is not working anymore as catalyst. This is not something new. The petrochemical industry know that since a lot of years. Indeed, normally in the catalytic processes, like for the production of more gasoline from a higher molecule of hydrocarbons, they normally burn off the carbon. So they take the catalyst, they burn off the carbon, and then it's regenerated and it can work again. In this case, we don't want to do that. We don't want to do that because the carbon that we are depositing on the catalyst can have a high value, and we can just use it and commercialize it. That's the point of the technology of the methane cracking. But which kind of carbon are we depositing? It depends, strongly depends on the characteristic of the process. So it depends on if you're working with a catalyst, if a thermal process, if you're working with a catalyst, which kind of catalyst. For example, we have different kind of carbon, like a carbon black, just really small particle of carbon, or carbon nanotubes. So these tubes of carbon that are generated normally with metal catalyst, because we have the deposition of the carbon on the catalyst and then the migration of the carbon inside the catalyst and then deposition at the end, the contact with the support that generates these beautiful carbon nanotubes or fibers. And also the temperature is helping the generation of one of these waste type of carbon deposited. But another question that you can think about is, okay, but there is the demand for all of this carbon. Here, just a brief example. We have more or less in 2023, 97 million tons of hydrogen demand worldwide. And if we think about producing this hydrogen with the methane cracking process, we will need 386 million tons of methane. That's okay, but then we will produce 289 million tons of carbon. That's a lot, of course. But how much? If you see the graph here, you can notice that the produced carbon compared to the demand of carbon nanotubes, carbon fibers, or carbon black is really high. So the result of this simple example is just to say, okay, maybe we cannot produce all the hydrogen with this process, but can be part of the solutions. But there is another point. The point is that we have more than one single demand of carbon. We can use this carbon also in other sectors. In this project, we are focusing on the steel making. And for example, if we compare that type of carbon with the demand that Andrea told us before, you can see that then is not too much, even if we produce all the hydrogen with this kind of technology, because the demand for the carbon is there. Of course, it depends strongly of the type of carbon that you need and what we can put in these industrial processes. But it's just to say that are not the carbon nanotubes or so are not the only demand for the carbon that we have in the industry. And just to conclude, let's just see a different type of, just a comparison between different type of hydrogen production routes. Here you can see some of them, which is the point. Normally the hydrogen is produced with the gray hydrogen is produced with steam methane reforming. And the point of this slide is to say, okay, but for producing 1 kilogram of hydrogen, you will need 2 kilograms of methane. And the energy requirement will be 6 kilowatt-hour per kilogram of hydrogen produced. And this will lead to CO2 emissions, not only for the one related to the energy requirement, but also from the CO2, because we have carbon in the feedstock, and so you will transform it, of course, in CO2 that goes into the atmosphere. One solution that we can see today is the water electrolysis. That is, of course, an interesting solution, because we are starting from a non-carbon feedstock, and then you can obtain 1 kilogram of hydrogen just from 9 more or less kilogram of water. It will require a lot of energy, and if this energy is not from renewables, that will lead again on the production emission of CO2, a good amount of CO2, as you can see at the end of this slide. But if it's completely renewable, you can decrease to zero this CO2 amount. There are any other solution? Yes, the one that I presented now is an interesting one, because differently from steam methane reforming, you are starting from less methane, is 4 kilograms for every kilo of hydrogen, but then the carbon that you are producing is not in a CO2 form, is not going into the atmosphere, or you do not require just technology to separate it and to then put it somewhere. You have just solid carbon, and you can do that, like store it or using as byproduct, as we said before. The energy requirement is lower than the electrolysis, and if you again use just renewable electricity, you can decrease to zero the CO2 emission from this kind of technology. So this is just an overview of why are we talking about methane cracking, and then my colleagues later we will show you more specific discussion about what we are working in H2STEEL. Thank you.
Thank you very much, Alessio. That was also a great presentation as well. And now we're gonna give the floor to Piercosimo Vedele, who's gonna be speaking about catalytic biomethane pyrolysis using biowaste derived catalysts. So Piercosimo, please, the floor is yours now.
Yes.
We can see your screen.
Okay.
And
Is in full
excellent.
screen mode?
Yeah.
Okay.
Excellent. Thank you very
Okay.
much. Go ahead.
Thank you, and good morning to everyone. So without further ado, I will go deeper into the fantastic world of the catalytic methane pyrolysis through carbon-based catalysts. Alessio was really complete in his presentation, so I will move really fast in this part. So nowadays, hydrogen is mainly produced through steam methane reforming, which is the most pollutant technique, but at the same time, the cheapest one. The demand of hydrogen will progressively increase all along the next 25 years in all the scenarios. And at the same time, we will have a decrease of the request of the hydrogen produced through steam methane reforming. Water electrolysis could represent a long-term only a long-term solution, because the energetic cost is really high. And for this reason, a mid-term solution could be represented by methane decomposition, which consists in the decomposition of the methane molecule into solid carbon and gaseous hydrogen. And the main advantages of this process are related to the production of highly pure hydrogen. Of course, it depends also on the conversion of the reaction, the absence of CO2 removal stages, and an easy way to store the carbon produced through this reaction. Of course, the main disadvantages are related to the high stability of the methane molecule. So it is an endothermic reaction, high temperatures and high energetic demand requests to conduct this reaction, and the lower hydrogen to methane yield compared to the state-of-art competitors, just like the steam methane reforming. Going deeper into our work, our way to reduce the energetic demand of methane pyrolysis is represented by the use of a catalyst, and there are different kinds of catalysts. As Alessio said, there are metal-based catalysts and carbon-based catalysts. The use of carbon-based catalyst is related mainly to the lower purchase cost and the extended stability and the lack of regeneration processes of this kind of catalyst compared to the iron-based catalysts. From our side, we tested several biochars, so carbon-based catalysts, which were synthesized by Record and which belong to the Suez sludge family. And this kind of biochar, the biochar produced from the Suez sludge, was subjected to different upgrading processes to produce catalysts with these different characteristics. In particular, the raw char was leached, then processed or milled and sieved in order to obtain obtain a catalyst with a pellet size lower and then activate it to obtain a material with different morphologic characteristics. As you can see, the different upgrading processes which were conducted on the char allows to obtain a different composition of the material. By increasing the upgrading, we are increasing the gravimetric percentage of carbon and reducing the amount of oxygen of our char, and at the same time reducing also the inner part of the char. And this is explained by the elemental composition that you can see on the table on the left, and is reflected also by the ER spectra of the biochar. As you can see from the fresh spectra, we have a reduction of the peaks, which are mainly related to carboxylic and hydroxylic functional group, which presents oxygen. But let's go deeper into the test phase. On the right, you can see the lab test bench that we use for conducting our tests. All the tests were conducted in a fixed bed using a fixed amount of catalyst and a fixed amount of an inert, an amorphous silica, to avoid the clogging of the reactor caused by the carbon deposition. And we can conduct three different kinds of tests. RAM test to evaluate the best of the 5 biochars that we are considering. So to make a screening of the biochar, and kinetic and the activation test to get the kinetic and the activation parameters. All the tests were preceded by a pretreatment phase in order to ensure the dehumidification of the catalyst. So let's speak about the first 3 biochars: the raw, the leached, and the millet leached. In particular, as you can see, the leaching increase the methane conversion. All the tests were conducted at 900 Celsius degree, by the way. The leaching increase the methane conversion and also change the onset temperature of the reaction. So through the leaching, we are able to activate our catalyst at lower temperatures compared to that of the raw char. And the milling increase again the methane conversion and allows to get higher steady state values of the conversion. And this is mainly related to the increase of the heat and mass transfer coefficients. Those results could be related also to the results of the nitrogen physisorption. So the increase of the activity of the catalyst could be related also to the increase of the specific surface, pore volume, and pore diameter of our chars. As you can see, the activation of the millet leach char allows to get a slightly higher conversion and the same steady state conversion. Let me use the pointer here. Okay. A slightly higher conversion compared to that of the millet leached and the same steady state. The pretreatment, the retreatment of the leached char instead allows to get a conversion which is comparable to that of the leached char and more or less the same steady state. So for this reason, no stability improvement can be detected from the processing treatments. The activation allows to reach a slightly higher conversion, and for this reason, we decided to proceed with our further kinetic and the activation tests with the millet leached char, because it represents the best compromise in terms of environmental impact of the upgrading and of course, the cost of the upgrading itself. The kinetic tests were conducted at several temperatures, and at each temperatures we changed the methane concentration. and we were able to model the reaction rate through a really simple power law. From each temperature, we were able to obtain a kinetic constant, and through the Arrhenius plot, we can get the order of reaction, the activation energy, and the pre-exponential factor. The order of reaction is close to 0.5 in agreement with that of literature typical of carbon-based catalyst, and also the activation energy, which is mainly related to the effect-driven mechanism typical of carbon-based catalysts. All the tests were conducted in triplicate to ensure the environmental reproducibility of the tests. And in particular, I want to point out that all the tests were conducted at low temperature for two important reasons. The first is that we want to ensure a gradient-less system, which works mainly in all its length in the same way, and at the same time we want to skip the mass transfer limitation of the system. And the same thing was done also with for the activation studies, which were conducted at low temperature, again to ensure the mass transfer, to ensure that we are in a kinetic regime. We used this kind of equation to fit the activity of our catalyst all along the time, activity which depends on the activation constant, Kd, m, which represents the dependence of the methane concentration of the activity on the methane concentration, and D, which represents the order of the activation. All the tests again were conducted in duplo in order to ensure the experimental reproducibility, and in this way we were able to get the activation, which an energy of the activation which is close to 92, which is really close to that of reaction, and it indicates that the activation of this kind of carbon-based catalyst depends only on the amount of carbon deposited on our catalyst, because the activation of the catalyst depends on the deposition of the carbon, and not on the quality of the carbon deposited. These kind of results were useful for the modeling of our fixed bed reactor. By solving through MATLAB this partial differential equation, we were able to get the profile of the methane conversion all along the time and all along the length of our reactor. Here you can see the main features, the main characteristics of the reactor, and from here you can see that our model is able to fit quite good the experimental results that we obtained from our test conducted at 820 Celsius degree. Of course, the model takes into account also the change in density and the change in particle size, which is related to the deposition of the carbon, but of course the conversion are really small, really small, and also the methane concentration is really small, so the amount of carbon deposited is few, and we don't have a huge change in density and particle deposition, but it is taken into account. Those results were useful also for a simulation of a new kind of reactor for conducting this kind of reaction, a moving bed, where gas and solid are sent to the reactor countercurrently. Here only to show that a sensibility study where you can see that by changing the residence time of a catalyst inside our reactor, we were able to reach different kind of conversion. Of course, by increasing the catalyst residence time, we are reducing the methane conversion, because the catalyst is characterized by lower activities, but at the same time we are also increasing the amount of carbon deposited on on the catalyst itself. Maybe here you can see better this reasoning. So at low catalyst residence time, we have higher conversion, but of course this kind of reactor characterized by really low residence time is also really it's not so easy to manage, but by increasing the catalyst residence time, we are also reducing the methane conversion, but we have also a reactor which is easiest to manage. Of course, this kind of technical study must be coupled with an economical study to evaluate which is the best trade-off from the point of view of the technical issues and from the point of view of the economical issues. So, in conclusion, we tested several biochars from the family of the sewage sludge, from the family of the sewage sludge, which were subjected to different upgrading processes. The leaching and the milling and the activation, of course, increase the activity of our catalyst. And in particular, the activation only slightly increase the activity of our catalyst. And for this reason, we decided to proceed with our further study with the millet leached, only because it represents the best compromise between performance, cost, and environmental impact of the upgrading. From the kinetic tests, we observe an order of variation and an activation energy, which is quite in agreement with that of the literature, and the activation energy, which is close to that of activation energy. And that's indicate that the activation profile is influenced only by the carbon yield, the amount of carbon deposited, and not by the pyrolytic nature of the carbon deposited. And those results were useful not only to simulate our fixed bed reactor, but also to make a simulation of a moving bed reactor, which represents the best way to scale up this kind of process, which elucidate the differences in terms of performance, of course, depending on the residence time of the catalyst inside our reactor. Thank you for your kind attention.
Thank you very much. Okay, now let's go to our next speaker, which is Niccolo Pezzati. He's going to be speaking about biowaste pyrolysis and chemical leaching for bio-based catalyst production. So, Niccolo, the floor is yours, please.
Thank you, Fernando, for the introduction, and good morning to everyone. So I'm sharing. Let me know if you can see the screen.
We can see the screen, but it's not in full size.
I'll go on presentation mode now.
Great.
Can you see it on presentation?
Not yet.
All right. Let's see.
Okay. There you go. Thank you.
Taking up the subject that was introduced by Andrea during the first presentation of the importance of decarbonizing the steel sector using replacing fossil coal with bio-based material substitutes. Here we will dive briefly into the technical aspects of the work that has been carried out on how it was possible to convert bio-waste streams into bio-based coal, which is suitable for steel makers. We, during the work, we focused on two different streams of bio-waste. One is sewage sludge, which derive from wastewater treatment plants. And the second stream that we used was an agricultural digestate that was provided us. So these two streams, as you can see here, we have analyzed multiple streams, not just one, but each category is pretty similar to each other. And both the streams work as good carbon source, but also present relevant ash amounts, which derive from inorganic species that are comprised in the feedstock, in the material. So these two aspects are relevant to us because the carbon is the source to produce a carbonaceous material to obtain the fossil coal substitute. But at the same time, the ashes in the material are harmful and detrimental to the steelmaking practices. In particular, the alkali metals, the phosphorus, do not comply with the quality requirements which are imposed by the steel makers. And also, one fundamental aspect of all of this is the phosphorus content in these biowastes, because apart from recovering carbon to produce the fossil coal substitute, if we are able to recover at the same time phosphorus, which is included in the critical raw material list by the European Commission, combining these two aspects together, it is possible to increase the added value of the process, delivering carbonaceous material and at the same time allowing to recover a strategic element with relevant markets and so on. So to accomplish this, we propose an integrated technologies solution in which first the biowaste streams are treated thermochemically by slow pyrolysis, which allows to unleash the carbon potential of the material, so removing the volatile matter and fixing the carbon in an inert form in the material. And later, combining this first stage with a second post-treatment, which is supposed to remove those harmful elements, so the ashes, which concentrate after the thermochemical conversion. And this upgrading is carried out with the aid of an acidic leaching, which delivers a low ash biocoal eventually. So at the end of all of this, we are able to obtain a solid product, which is an upgraded biocoal, which can meet the quality requirements for steelmaking practices, and an acidic leachate, an aqueous phase from which we can recover the phosphorus as a critical raw material, and adding both economic and environmental value to the solution. So the first stage of this integrated process is the slow pyrolysis that we carried out at a pilot scale here at Record. and for which we have first optimized the conversion conditions at a laboratory scale, and afterwards we have replicated those in the pilot unit. So the parameters that we have focused on are temperature, the residence time, and the heating rate of the conversion chamber. So we have converted both the biowaste streams at 550 degrees Celsius with a residence time in the conversion chamber not overcoming 1 hour, and fixed heating rates of 20 degrees Celsius per minute, which is typical for slow pyrolysis processes. The output of this conversion, of course, is focusing on the yields on the solid products, so the raw biochar, which we can obtain from the thermochemical conversion. And as you can see here, when processing the sewage sludge, the solid yield is slightly higher than when processing the agricultural digest state. So we have 51% solid yield against 39% solid yield, as you can see in the pie charts. And this is due to the higher ash amount in the sewage sludge than in the agricultural digest state, which are not degraded by thermochemical treatment, and so concentrate in the solid product, giving a higher solid yield. Apart from, of course, assessing mass balance of the process, we have also assessed the energy balance of the process. And as you can see here, we are able to recover 45% of the energy initially comprised in the feedstock of the agricultural digest state into the raw biochar, which is produced from that particular biowaste, whereas in the case of processing the sewage sludge, 39% of the energy which is comprised in the sludge eventually ends up in the raw biochar. So the two biochars that were produced, as I have just described, were also characterized. And here I want to draw the attention on the key aspects of the slow pyrolysis outputs. So first of all, the thermical treatment allows to reduce the volatile matter in the solids, going below 20% threshold, so we can eventually see a 16% volatile matter content in the raw biochar from the sewage sludge, and a 13% volatile content in the raw biochar from the agricultural digest state. The most relevant aspect here, though, is the increase of the ash content. In particular, in the case of processing the sewage sludge, we almost touch 60% ash content in the raw biochar, which is a shortcoming of this first stage, but which we can fix later through the chemical leaching. In the chart in the middle here, you see a Van Crevelen diagram that shows you how it is possible to convert the bio waste into high rank coals. So moving from the region of the biomasses on the top right of the diagram down to the region in the left bottom corner next to the coal and anthracite region. And also during the thermic conversion, we see how the caloric density of the material change. In particular, when treating the agricultural digestate, it is possible to increase the caloric density from the biowaste to the raw biochar, thanks to a lower amount of ashes and a higher carbon content, which becomes fixed carbon in the biochar. Whereas it is relevant to notice that when treating the sewage sludge, the caloric density, so the higher eating value, decrease. And this is because of the high ash content in the sewage sludge, which creates a dilution effect despite of fixing the carbon matrix in the substrate. And also here I reported the characterization, so the elemental profile of the two biochars. So focusing on the silicon, the phosphorus, the iron, which are particularly in the case of the treatment of the sewage sludge, we reach very high concentration levels. As you can see, silicon in the raw biochar from the sewage sludge is almost 10%, as well as iron. Phosphorus in both the raw biochars is instead around 2%. And this is important because we want to recover it later. So to overcome, as I was saying, the shortcomings of having high hash content in the raw biochar, we create this solution in which we are able to remove the ashes from the solid with the aid of an acidic treatment. The acid reagent that we used is nitric acid. So the treatment, which has been performed on a pilot scale, as you can see here in the clip, is performed at a temperature between 70 and 80 degrees Celsius with a dwell time of 60 minutes and an acid to char ratio which can range between 0.4 and 0.6. And the treatment, as I was saying, allows to extract the inorganic elements from the solid into an aqueous phase. And as I'm reporting here, it is possible to achieve a 63% degree of demineralization when treating the raw biochar from the sewage sludge, whereas this value is even higher, equal to 73% when treating the raw biochar from the agricultural digestate. And all in all, so we reported, we have the yields of the integrated process. So first, the pyrolysis stage, gives a 51% solid yield when treating the sewage sludge and a 39% solid yield when treating the agricultural digestate. Then the leaching post-treatment has a solid yield of 55% when treating the raw biochar from the sewage sludge and 69% solid yield when treating the raw biochar from the agricultural digestates. And eventually we have respectively a 28% solid yield and a 27% solid yield for the overall process. And here, so I'm presenting you the key indicators of the integrated process, which is first, how the post-treatment can reduce the ashes from going from the raw biochar to the upgraded biocoal. As you can see here in the two column charts, the ashes increase during the first stage of the treatment. So from the biowaste to the raw biochar, but afterward, the acid post-treatment can again reduce this level and bring it down to acceptable values. Whereas for all those elements which we consider detrimental for steel making practices, we see here how it is possible to sensibly reduce all of them apart from the silicon. So the post-treatment is only ineffective on the silicon, which concentrates through the entire process, whereas all the other elements, so the iron, the alkali, the earth alkali, metals, the heavy metals as well, and mainly the phosphorus are extracted in the acid leachate, so leaving the solid products free of any sort of these contaminants. And we calculated the efficiency at which we can extract these elements. So we have an idea of the recovery rate of these key elements, and in particular, phosphorus can be recovered at a 96% rate during the treatment of the char from the sewage sludge, whereas it is almost quantitatively recovered during the treatment of the char from the agricultural digestate. So all of these enables to increase the added value of the solution proposed. So drawing my conclusion, the work that has been carried out here at Record validated the possibility to scale up this integrated process, validated the slow pyrolysis stage, showing the difference of the solid yields between the sewage sludge and the agricultural digestate, and also the different amount of energy which can be recovered in the products, and later on demonstrated so validated the effectiveness of the post treatment, which allows to abate the ash content of the raw biochars and remove harmful elements and eventually opening a route for the recovery of a critical raw material such as phosphorus. So that's it on my side, and I thank you for the attention.
Thank you very much, Nicolo. Thanks also for having some videos on the presentation. I think that made it a little bit more interesting. Now we're gonna go with our last speaker, which is Amer Sanat. He's gonna be speaking about results from the catalytic methane pyrolysis proof of concept system. And afterwards, we can have a Q&A discussion. So please, Amar, the floor is yours, and we can see your screen.
Okay, perfect. Thank you so much, Fernando. Thank you for the introduction. Please let me know if you also can see it in presentation mode.
Yes.
Yes,
absolutely.
okay, perfect. Okay, so good morning, everyone, and thank you all for joining in today. With this presentation, as Fernando was saying, I'll be concluding this webinar, and we hope you are enjoying it so far. And by presenting the results from catalytic methane pyrolysis proof of concept plant. My name is Amr Sanat. I'm a PhD student at Polytechnic Torino, and I'm an R&D engineer at the Record. H2STEEL project brought experimental trials from lab scale to proof of concept pilot scale. Results from the lab scale batch system at Record shown on the let me use the pointer. Results shown in this picture, and also the results shown presented earlier by Pier Cosimo that are present in Polytechnic Torino have helped shape the plant we will be exploring today, which is a continuous biocoal-based catalytic methane pyrolysis unit. Okay. The following is a brief description of the plant, and it is based on a moving bed reactor with a volume of roughly 6.5 liters. It has a total inlet flow rate of 2 normal meter cube per hour of gas and a solid capacity of 150 liters per experiment. This catalyst amount is enough to conduct experiments and reach steady state for several hours. The precise number of hours, of course, is obviously depending on the operating conditions, and it usually is enough to show the stability of the process itself at those given operating conditions. There are two separate lines that are divided into 12 functional subunits, as shown in the block flow diagram shown here. A line that is dedicated for the catalyst, and another is dedicated for the gas, with the reactor as acting as the crossroad of both lines. The catalyst line starts with the catalyst storage at the 150 liters hopper, which is in turn placed over a load cell, allowing for precision monitored feeding from the hopper into the heating screw. The heating screw is, as the name suggests, is heated electrically and is used to heat up the catalyst to a temperature up to 900 degrees Celsius. The catalyst is then moved into the reactor where the interesting stuff happens. And here the gas is also fed into the reactor from the gas feeding line. And then allowing for the reactions to happen, and the necessary reaction for the production of hydrogen and the deposition of carbon. After which the carbon is moved into the cooling and discharging screw. It's a screw that also controls the cooling of the system, and it's also and the gas goes through the gas cooling filtration and then gas management system, and then in turn later on it goes into the micro GC for gas analysis and further reductions. By carefully controlling the dosage, of course, of the catalyst by the doser and the screw rotations, we can control the level in the bed and maintain it at the desired value for residence time required. On the other hand, the outlet gases, yes, are treated and then went to the gas management for the analysis. Okay, so when we ask, what are the advantages of such a system? Well, first of all, it's a fully monitored unit that allows flexible investigation of various operating conditions that can be adjusted to find the proper trade-off between hydrogen production and catalyst renewal. Since catalyst is continuously fed, as previously mentioned, for the necessary duration of the experiment, it is continuously renewed as carbon deposits on its surface, causing possible deactivation. Interestingly, though, this deactivation is not seen, as it usually is, as a limitation, but rather as a valorization of the catalyst, since the product is then a carbon-rich biocoal instead of a normal standard biocoal. Another important feature of this plant is that it is designed to test conditions with up to 100% methane at the inlet, allowing for real-world conditions testing. The continuity of the plant makes it one step closer to demonstrating the possibility of such a process on an industrial level, or in its application in an industrial level. Okay, and here is a list of the operating conditions and parameters for conducting an experimental investigation and in this plant. And the list includes all main parameters from catalyst shape and sizing to available reaction volume range and catalyst residence time within the reactor. As previously mentioned, the plant is designed to operate under up to 2 nanometer cube per hour of gas at the inlet, which can be a mix, either mix of methane and nitrogen or pure methane, and it can also be natural gas used. Here's the hopper we were talking about earlier, where the gravimetric feeder, where the carbon is, the catalyst is at first charged, and then when going through the heating screw, and then the reactor, and then further to the tank at the end of the line. So, as per the catalyst preparation, as catalyst is prepared in record, as was mentioned also earlier, and starts from the production all the way to the preparation for test. And the main preparation steps after the production is pyrolysis, which requires at least a 50 kilogram of biocoal in powder form that is dry mixed with 3 to 4% of starch. Hot water is then added and pellets are formed in a 30 kilogram per hour unit that is shown in this figure. And the pellets are produced from this pelletization process, as you can see, it's presented in the pictures on the right-hand side. And we finally get to the interesting part for most people, which are some of the results of the various trials. Okay, as mentioned earlier, one online gas monitoring is allowed at the gas handling unit. Thanks to the micro GC connected for continuous monitoring of the gas composition, the results of one of the tests conducted with commercial carbon is shown in the figure on your right-hand side. On the left-hand side instead, we have a schematic for the reactor with the position of the multi-point thermocouple, the different temperature sensors that can also monitor the situation within the temperature of the within the reactor itself. It is evident, however, the results of this test shows on the right-hand side in this graph that the steady state conditions can be achieved after, of course, a transition state, but eventually the steady state is achieved and is maintained for more than an hour. From gas composition at this outlet that are obtained from the micro GC, we can then calculate the what's called the methane conversion, and using this equation, which is basically evaluating the percentage of consumed methane with respect to the one at the inlet. And this is the last slide of my presentation for today. So where I would like to show you the results from the 4 different experiments and their relation to one another. All these experiments were conducted at the maximum gas inlet operating conditions of 2 nanometer cube per hour and 20% methane inlet percentage, with the other 80% being nitrogen. In light blue, you can see the commercial carbon used as a catalyst, as a benchmark for the other catalysts that are then produced and used within the H2STEEL project. Please note that the shown percentages are normalized relative to the highest one and do not represent real point percentage, but rather used to show how the different operating conditions can influence methane conversion, calculated using the formula shown in the previous slide, of course. The commercial catalyst shows a decreasing conversion trend as the residence time of the catalyst within the reactor is increased. Of course, using the same operating conditions, so the same gas velocity, the same gas inlet and the same reactor level. This is in line with results obtained from lab scale trials and results in literature. The dark blue point, the one over here, it represents the it represents the catalyst that was produced by H2STEEL within the H2STEEL catalyst, which is also tested at 20 minutes estimated residence time. These results, although they show although shows a higher relative conversion of commercial carbon with respect to the in-house H2STEEL one, it shows a relatively close value to commercial ones, keeping in mind that one of the very important aspects of this is that it is derived from waste, as was mentioned several times also by my colleagues. And so it's a biocoal and not a fossil-based one, and that it did not pass through the same pre-treatment as those produced commercially and used for this experimental trials. Of course, an enhanced catalytic performance might be achievable with further pre-treatment before the usage. For example, further activation or physical activation or something, or a trade-off between higher performance and lower treatment cost can be favored. This is basically a choice to be made for the future. And by this, I have concluded today's pre-presentation. I think I am more than in time. Yes, I still have some time. Hope you enjoyed it, and that we have managed to show you a little on how industrial defossilization can become a reality. If you have any questions, of course, I'll leave now the floor to Fernando to handle the Q&A session. Thank you so much.
Thank you, Omer. Thanks everybody here for bearing with us until the end of the presentations. I think it was a very nice session, and now it's time for you guys to let us know if you have any questions, or if not, we can just move on and we can say goodbye to the rest of the people. So let me check here in the chat if we have a question. Well, not really. I don't know if anyone here of the part of the audience has any question for our speakers, or even if it's a question from within one of the speakers to another speaker. But yeah, let's wait a couple of minutes to see that anyone shows a question. If not, I think we can conclude the session. Maybe anyone wants to add something else? Well, I don't think we have questions for today's session. Anyways, for this session, we will have it uploaded in our YouTube channel and promoted on our social media channels. So hopefully, if you were not able to see it today, you will have the chance to take a look at it later on. So thank you very much for being here with us today, and I hope you have a good one. Thank you very much to all of the speakers, and we'll see you next time.
Thank you. Have a good day.
Thank you.
Fernando. Have a good one.
Thank you.